Alright, in this lesson we're going to talk about universal gravitation. It's the last lesson of chapter 3 and for our first major unit. Okay, so I want to cover a couple things. Universal gravitation is one thing, but I also want to go over two terms that we haven't talked about yet. Apparent weight and artificial gravity. So let's start with apparent weight. So imagine you're in an elevator. And you're curious about whether or not your weight will change when you're in the elevator. And let's go say a big elevator like the CN Tower. We go to the elevator at the CN Tower. And so we bring a scale with us. Well, what does a scale actually measure? It tells you your mass, right? But it doesn't actually measure your mass. It measures the normal force, right? The contact force between you and the scale. The scale just has springs in it, and it measures how much those springs are being compressed. So it's measuring a contact force. Now, if you're just standing on it and the elevator is not moving, well, you have the force of gravity acting on you, of course, and you have the normal force pushing up. And so the normal force equals the force of gravity, and your scale is going to do some calculations because the people who programmed it said the value of g is 9.81 meters per second squared, or newtons per kilogram. And it does calculations and it spits out your mass. This is why you actually can't take a scale to the moon and weigh yourself. And you'd have to reprogram the scale to tell it what the value of the gravitational field strength is on the moon. Or else it would spit out the incorrect mass. Okay, because your mass is not supposed to change when you go from the Earth to the moon. Only your weight is, or the force of gravity. But our scales measure the normal force. So here's the question. We get into the elevator at the CN Tower, and it starts to accelerate up. As it's accelerating, not when it reaches some constant speed, but as it's accelerating up, what happens to the reading on the scale? Does it increase, decrease, or stay the same? Think about that. Okay? If you need to pause, that's fine. The next question is, as it's moving at a constant velocity, what happens to the reading on the scale? Increase, decrease, or stay the same? And the next question is, as you get closer to the top, it accelerates downwards, so it's slowing down. When that happens, what happens to the reading on the scale? Increase, decrease, or stay the same? Finally, right as you're about to reach the top, terrible tragedy occurs, and the cables snap, and all the safety systems break, and the elevator just drops. And as it's dropping, you think to yourself, what's the reading on the scale? Does it increase, decrease, or stay the same? Okay. So if you need some time to think about those, think about them. What we're going to do is look at question number 1. We're going to try and answer these questions. Question number 1 says, an elevator accelerates upwards. It's the exact same thing we talked about. We can make this the entire if you wish. It's just I give you numbers. So initially the acceleration is 1.5 meters per squared up. Then we're at constant velocity, and then accelerates down at 0.9 meters per second squared. I don't have the example in this case where the elevator loses its cable, but if it falls, well, then the normal force disappears, right? Both the only force acting on the occupant and the elevator is gravity, and so you both fall at the same rate, 9.81 meters per second squared. Without no normal force, you would read your weight as 0, so you would be in free fall. But what about when it's accelerating upwards? Now, think of it qualitatively. If it accelerates up, it's moving up and pushing up on you. Your inertia, kind of wanting to stay where it is, almost feels like it's providing an extra downwards force. Okay, now there is no real force it's providing, it's just your inertia, right? If you want to, you can go into that accelerating frame of reference and create your own fictitious force, but we're not going to do that. We're just going to solve this problem with these forces, the real forces, and we're going to say the sum of all forces equals mass times acceleration. Now acceleration is up, so let's make up our positive direction. That means we have the normal force minus gravity, which is mg, equaling ma. And now the scale is going to tell you your normal force, so that's what we're solving for here. So the normal force equals, well, mg plus ma. So if we factor out a mass, it's just g plus a. So that upwards acceleration is almost like it's adding to the 9.81 in gravity. Like mathematically, that's what it looks like it's doing. It's increasing the force of gravity that's acting on you. Okay? And therefore, the normal force should increase. Now, if you want some numbers, we can actually get a number here. Our mass is 75 times by 9.8 plus 1.5. And we get a weight, apparent weight of 847.5, rounded to two significant digits, 8.5 times 10 to the 2 newtons. Okay. Next question, if it's moving at a constant velocity. Well, if it's moving at a constant velocity, then there is no acceleration. So that would be 0. And your normal force will equal gravity. I think we all could have guessed that. That's an inertial frame of reference, and all of Newton's laws maintain themselves there. Okay, now what about when it's accelerating down? Well, in this case, let's change our coordinate system, and we'll make down positive. Therefore, we have gravity, mg, minus the normal force equals ma. Rearranging the solve for the normal force, and we can factor out from mass, we get g minus a. So again, it seems like the acceleration is now making gravity a little bit less on you. And if we plug in our numbers, which is 75 times 9.8 minus, what's our acceleration, 0.9, we get 667.5, or 6.7 times 10 to the 2 newtons. So indeed our weight has decreased. Okay, so that's apparent weight. The next thing I want to talk to you about is artificial gravity. Now it sounds really sci-fi, but it's not. It's actually really easy to create. How many of you have actually been on one of those carnival rides where you go inside something that looks like a flying saucer and you stand up against the wall and then it starts to spin really fast and you can't see outside? So my first time going on that thing, I thought, oh, I'm going to get dizzy and throw up. But I didn't get dizzy at all because you don't see everything spinning on the outside. But you do get pushed up against the wall. Why is that? Okay, and this is going back to the centrifugal force. You're in a non-inertial frame of reference, a rotating frame of reference, and your inertia wants to keep going where it's going. And so you feel like you're being pushed outwards. Okay, this is a fictitious force, but it's a force you feel nonetheless in your frame of reference. So we can simulate this in space. If we took that ride and put it up into space, there would be artificial gravity. Right? If you're far away from any gravitational force, or if you're in orbit and undergoing free fall around the Earth, you don't have that downwards force that you would have if you went on the carnival ride at the local fair. Right? If you're in space, the only force you have is that centrifugal force outwards, and so you could actually start walking along that wall. And if you get the speed and the radius right, the speed for whatever radius your ship is, it would feel no different than being on Earth. You can set it to feel like 9.81 meters per second squared. Okay, so it's really, really simple and easy to do from a physics point of view. The hard part is the engineering and the politics and the cost of it all. That's why it's never been done, right? It would be very useful because astronauts who go into space lose muscle mass and bone density, so even to have one room that spins, which can be their exercise room, would be really great and really expensive. So that's the only reason why we've never actually created artificial gravity. All right, last, Newton's law of universal gravitation. So we've talked about gravity. Gravity pulls us down to the Earth. But it's not just the Earth. Right? The moon orbits the Earth. If you went to the moon, you'd also be pulled down to the moon. The Earth is also pulled into the sun. Right? Everything has a sort of gravitational attraction to everything else, it seems. Well, what about me? Do I have a gravitational attraction? Of course I do. Right? I'm being pulled to the Earth due to a gravitational attraction. Newton's third law says action and reaction, meaning I'm pulling the Earth with the same force the Earth is pulling me. So I must be supplying some gravitational attraction to the Earth. How do we calculate this? Well, being on the Earth is easy to calculate. You just write Fg equals mg. But what if I don't know g? And what if I go to the moon and I don't know g? Or what if I wanted to calculate the force of gravity between the Earth and the moon? Or between the Earth and the sun? Well, Newton said that if you have two objects with a certain mass, let's call this m1 and m2, and you separate them, you separate their centers by a distance which we'll call r, the force of gravitational attraction that acts on them, I'm going to label this big G, equals this proportionality constant, capital G, times the two masses of their object, divided by the distance between them squared. So G is a constant. It's different from little g though. Capital G is a universal gravitational constant, and it equals 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So yeah, the units don't really make sense, but they're there because it's a proportionality constant. We want to create units of Newton if we input kilograms per meter squared. And that's the proportionality constant that's required. And it never changes, no matter where you are. It's not like small g where it's different depending on whether you're on the Earth, you're in orbit, you're on the moon, Mars. This will be the same everywhere in the universe. Okay? And this tells us that any two objects with mass are gravitationally attracted to each other, proportional to their masses. So the larger the mass, the greater the force, and inversely proportional to their distance squared. So the closer you are, the greater the force. Okay, and that is squared. So that's a very, very big relationship there. Okay, so let's try a question with that. Question number 2. It says the International Space Station, the ISS, orbits the Earth at a height of 408 kilometers above sea level. That's quite amazing though, isn't it? It's only 408 kilometers up. I mean, you could easily drive 400 kilometers on a highway in 4 hours. It's not that far away, considering it takes 3 days for high-speed rockets to get to the moon. How fast does the ISS need to be moving in order to maintain this altitude? Okay, so we talked about if you want to be in orbit around the Earth, you need to be moving fast enough, right? Or else you're just going to fall down and hit the Earth, right? You need to be able to go around the Earth as the Earth curves away from you. So we want to know speed. Now this is undergoing centripetal acceleration, right? If you're on the ISS, you're going around the Earth. Okay? And the only force acting on you is gravity, which is directed to the center. So we'll make that our positive direction because that's also the direction of acceleration. And we'll go to Newton's laws. The sum of all centripetal forces equals mass, and that would be the mass of our free body diagram, which in this case is the ISS, times centripetal acceleration. And the only force acting on us is gravity. We can calculate that with our new equation. G, I'll use big M for the Earth and small m for the ISS, over times small m over the distance between them squared equals mass of the ISS times AC, and we're going to write AC as B squared over R. Okay, well, this is cool. The mass of the ISS doesn't matter. If it's at a certain radius from the Earth, it needs to be going at a certain speed, no matter what its mass. So rearranging, we can solve for V, which would be orbital velocity. One of the R's will cancel. And it's just the square root of Gm over R. And that will be orbital velocity. Okay, that's an equation you will not get on your tests. Okay, it is the equation for orbital velocity, but this is where we start from. Okay, so solving, put it in your calculator. If you need to do it in a couple steps, that's fine because it's a lot of big numbers. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And your radius, now this is very important. In this question, it tells you the radius of the Earth. Okay, but you're also, let me actually write down these numbers. C is the square root of Gm over R. So we have G, 6.67 times 10 to the minus 11. We have the mass of the Earth. And we have radius. The radius of the Earth is 6.38 times 10 to the 6 meters. But the ISS would be that radius of the Earth plus its altitude above the surface of the Earth. So in this equation, we're talking about the distance between the center of the Earth and the ISS. So we need to take its radius and add its altitude, which is 408 kilometers, or plus 4.08 times 10 to the 5 meters. If we plug all of that in, 6.38, we get 7,666, or how many significant digits? 3. So 7.67 times 10 to the 3 meters per second. That's pretty fast. 7,670 meters per second. If you want to know what that is in kilometers per hour, multiply that by 3.6. It's fast. Okay, that's a lot. That's why a lot of the times if you watch a rocket launch that wants to go into orbit, it doesn't go on straight up. It goes sort of on a curve because it only needs to go up a few hundred kilometers. In fact, our atmosphere only goes to about 100 kilometers above the surface. So once you're above that and there's no more air resistance, in order to get into an orbit, you need to achieve very high speeds horizontal so that you can actually orbit. So that's why they go up like this and then they curve because they want that horizontal speed. They're not just going to go up and then turn and go this way. Right? It's more efficient to do a curve like that. All right, then it says, what's the gravitational field strength for astronauts on the ISS? So a lot of the times I get students say, oh, it's 0 because they're floating. No, they're floating because they're in free fall. Right? They're always falling. Okay, and the ISS is always falling. If we want to calculate the gravitational field strength, what we can do is set our two equations for gravity equal to each other. I mean, it's perfectly fine to do that. They both, if you wanted to calculate the gravitational force or the weight on an astronaut, you can use either of these two equations. This one's fine to use. You just can't use 9.81 for G. because it's not. But if we wanted to determine what it is, this is a great way to do it. So we'll have G, and that will be the Earth, and this will be the ISS or an astronaut, whatever you want. You'll see it's going to cancel anyways. Over R squared equals mg. There you go. It's canceling already. And so you can calculate your gravitational field strength, or you can calculate the gravitational field strength for any location from any object using this equation. All you need to know is the mass of that object and the distance from it. So if we were to plug in what we know into this equation, so we have G equals and 6.67 times 10 to the minus 11. Then we have the mass of the Earth, 5.98 times 10 to the 24. All over the radius squared. Again, you want to add it. So 6.38 times 10 to the 6 plus 4.08 times 10 to the 5. I put them both in meters. Make sure you're not doing meters plus something in kilometers. Right? They're both in meters. And this time we're squaring that. And this will give you a value of G. So 6. And plug it into your calculator. Make sure you all try to plug this into your calculator, because when students come up to me with questions about these types of questions, 99% of the time their work is fine. It's just they punched it into a calculator. I think they're huge numbers that we're punching in here. So make sure you try it and you're familiar with your own calculator and how to punch in numbers this big on it. I almost made a mistake myself. Square. 8.6565. I'm going to two significant digits, or to three significant digits. 8.66. So it's not that much less than it is for people on the Earth. So remember, they're only 408 kilometers up. They haven't left the solar system or anything. So instead of 9.81, it's 8.66. All right, just one more question we're going to do. That's question number 3. It's a tricky question, but it's a question I like because it compares things. Okay, when you see an equation like this one, universal gravitation, and now we're to say, well, let's say I doubled the mass of one object. What happens to the force? Well, you should know it doubles. What if I doubled the distance between them? What happens to the force? Well, in that case, it reduces by 1/4, right? By the inverse squared. Now, this question is not as simple as those two examples, but it's the same type of question. And it says, at a certain distance above Earth's surface, the gravitational force on a certain object is only 2.8% of its value at Earth's surface. Determine this distance, expressing it as a multiple of Earth's radius RE. So here's what I want to look at. I want to look at this as a proportionality, not an equation like this. Okay, so you can't plug in numbers into this. It's a proportionality. But what you can do is see how one changes. Now this one says the gravitational force. Okay, so here's the equation that we're using. Now what's actually changing? Looks like just R is changing. So let me write this like this. It's perfectly fine. You may say, oh, you've left out math. Well, no, I haven't. This one says that gravity is proportional to both masses and inversely proportional to R squared. If I simply say gravity is inversely proportional to R squared, that's not an incorrect statement. Gravity is inversely proportional to R squared. This is us considering just this relationship because we know the masses are staying the same. Now let's look at a little bit about proportionalities. Let's say I were to say A is proportional to B. Well, what does that mean? If A doubles, B doubles. I can write this as a ratio. I can say A2 over A1 equals B2 over B1. Right? I compare what A was before to what it is now, and what B was before and what it is now. If I write it as a ratio, I can write it like this because I know they increase together linearly. Right? And so if A doubles, then this becomes 2 over 1. B also doubles, and so this ratio is 2 over 1. If I were to say this, A is proportional to B squared, I can say this ratio is true. B2 squared over B1 squared. Similarly, if A is inversely proportional to B, well then I just flip one side of the equation. Like A2 over A1, and I take the reciprocal over here and write B1 over B2. Okay? This is how we're going to solve this problem right here. So if I have this, where FG is proportional to 1 over R squared, I can say FG2 over FG1 equals, and first I'm going to flip them, so I'm going to do R1 over R2, and I'm going to square them both. Okay, so what's happened? We've had something on the surface of the Earth move up to another point where the gravitational force is now 2.8% of its initial value. So what does that mean? It means this is now 2.8% of that. So I can write it in terms of that. I can say Fg is 2.8? Yeah, 0.028 times the force of gravity initially. That's what percentage means, right? It's a fraction of 100, right? So just divide by 100, and you can get rid of the percent sign. So F2 is 2.8% of F1 over F1, and that's great because now they cancel. R1, our initial one, is just, I'm going to write RE because it's just the radius of the Earth, over R2. I don't know what that is yet. That's what I'm trying to solve. But now I can rearrange and solve this. I can say R2 squared equals RE squared over 0.028. And then I could take the square root of that. Both sides. Just continue it up here. So R2 equals RE over the square root of 0.028. And then you could say, oh, I'm done, because it just says express it as a multiple of Earth's radius RE. But what exactly were you trying to find? It says at a certain distance above Earth's surface. So what we just calculated was this. That's R2. What it's asking for is this, A, the altitude above Earth's surface. So R2 is essentially RE plus A. So R2 is RE plus A, which equals this. And we just want to solve for A. So again, solving for A now, bringing RE to the other side. And we can even factor out an RE, because it says express it as a multitude of that. You get 1 over the square root 0.028 minus 1. Because that 1 comes from the RE that we brought over and, well, subtracted on the other side. Okay. Now you can plug in that bracket onto your calculator. 1 divided by the square root of 0.028. Subtract 1. And you get 4.98. We can round that to 5. So A equals 5.0 RE. Okay, so that means if your altitude was 5 times Earth's radius, the force on you would be 2.8% of what it was when you're on the Earth. Okay, and that's it for Chapter 3 and our first unit.